So now we're finally ready to start talking about deep neural networks. We've seen how a single neuron works, and we've seen how a network of neurons can be used to predict multiple outputs. Now we want to extend that concept to be having multiple layers of neural networks chained together in a way that we can add complexity to our model. So that way we can encapsulate more of the behaviors of our underlying data set in the model and explain more of their variation. Going back to our previous example from the last lecture, we're looking to find a way that we can detangle those apples, which were kind of stuck in between the bananas and the grapes in our feature space. So we want to find a model that can encapsulate that kind of nonlinearity. So what do deep neural networks look like? How do they behave? Well, you've already seen images along the lines of this, right? Where we were just looking at a single layer. So something where we're just looking at the first section here with the light blue and the first section of the purple, where you know exactly everything that's going behind the scenes here mathematically, right? We know that we have a 3-element feature vector that this model takes in. We know that it's doing a matrix vector multiplication and then adding in biases for each one of these neurons. We know that it's then applying some sort of nonlinearity to come up with 4 outputs at the end. Well, what a deep neural network does is it just tacks on an extra layer where it couples the outputs from the previous neural network into the next one. So now we have these 4 intermediate outputs. Let's take them as inputs to our next layer, and so on and so forth. So this next layer has 4 inputs and 3 outputs. So you know that's a 3x4 matrix. It does the matrix vector multiply, add the bias, perform the nonlinearity, and move on. In the end, this model as a whole has 7 outputs with 3 inputs and goes through 3 layers. So what does this mean intuitively? Can you get a sense of how this operation works, and what does it do to the data as it processes it? How is it able to encapsulate more nonlinearities? Well, one way to think about this is with this cartoon of data that I have drawn here. The command to plot it is commented away, just so that way we can look at the data without worrying about how it was generated. The generation isn't the important part. The important part is how we're going to kind of manipulate it in a way that's somewhat akin to how a neural network does. So these are our original data, and we want to fit a model that can encapsulate some of these nonlinear behaviors that you see here. So the first step in our neural network, our deep neural network, right, the first layer, the first thing that happens is you do a matrix multiply and add a bias. That's a linear operation. So you can imagine that linear operation is doing something like this, where it finds a line that explains the most variation and does some sort of rotation and scaling. Well, that rotation and scaling then gets placed in such a way that you end up with a nonlinearity that can explain yet more variance of this model. So that allows you to not only explain some linear behaviors, but also some nonlinear behaviors. If we didn't have this nonlinearity and we just passed it to another linear system, well, the composition of 2 linear transformations is just another linear transformation. There's no additional complexity that you're adding to the system there. So adding a nonlinearity, however simple, in this case, it's just a piecewise linear function that's kind of a flat and then a ramp and then a flat. Doesn't matter what this nonlinearity is. The key thing is that there is some nonlinearity that allows the system to not completely collapse down into a single layer. So with the linear transform, we can then effectively fit a nonlinear component to this, and then it allows us to explain yet more of the data. So after this first layer of our neuron, this one output might look something like this, where we've explained the first section of the data set. And there's yet more data to be explained. So the next layer, what's that going to do? Well, first, a linear transformation. You can imagine it scaling and rotating and shifting things around in a way that the next nonlinear transformation, so this is after that linear transformation, so it's scaled and transformed in a way that the nonlinearity is able to explain more of the variance of our data. And then you can, account for this in our data set and subtract it away. So after our final second layer, we end up with data that are beginning to be explained, and we have a model that can generate these data. So the ideal end result here would be a completely flat line, right? That would mean that we've accounted for our entire data set. Well, this is just a cartoon. Hopefully it gives you a little bit of a sense of why the nonlinearity activation function is important and how these things stack together. There's a few things that I kind of glossed over as I did this. One is that I explained it as an iterative process, right? First we fit the linear system, then we fit a nonlinearity to it. Well, that's not at all how it's working. It's doing gradient descent, and it's figuring out which parameters of our linear system can be nudged in a way that our nonlinearity is able to explain more of the data, right? And so these two things happen hand in hand in a way that's very efficient and allows us to walk down the slope of our loss function to find a better model as we tune these parameters. So that's kind of a hand-wavy explanation of what a deep neural network does. This is just one output, right? We would have lots of outputs, and all these outputs are commingling together through each layer, can be densely connected to one another. So how does this look like in Flux? And can we take this and extend it to our previous example and allow us to do a better job of explaining the data there? So let's load those data. This is exactly what we did last time, so I'm not going to explain it much besides to say that we end up with a vector of our feature labels that has our apples, bananas, and grapes in it, and a vector of our outputs. I'm sorry, I said that funny. Our feature vectors with our apples, bananas, and grapes, and our output vectors, which are these one-hot labels that have, one true element and the other two elements are false. So the first element is true for apples, second for bananas, third for grapes. So those are our data. And previously, we had just used a dense neural network with 2 inputs and 3 outputs and a sigmoid activation function, so this was our nonlinearity, as our model. Now I want to construct multiple layers and chain them together. How would you do that? Well, you can just construct multiple dense neural networks, right? And then if we take our first data point, so x is of 1, right? Remember that this is a 2-element data point. The first is our mean amount of red in some image that describes, in this case, an apple, because we're at the beginning of our data set. And the second one being the mean amount of blue in our image. So this is our feature, and we can evaluate the first layer with that feature vector. Oops, if I spell it correctly, layer 1. So this layer has 4 intermediate outputs, or 4 hidden outputs. And of course, if you evaluate the layer on the first feature vector, you end up with a 4-element array. Now we've not trained this at all, right? So it's just going to output gibberish, but you can see that the shape here is right. And then you can pass that to layer 2 and evaluate layer 2 with those 4 inputs now. And you end up with the 3 outputs that we would expect. So of course you can chain these all together with layer 2 of layer 1 of your features. And that gets tedious, especially if you have lots of layers. So Flux, of course, provides a nice convenient chain function that allows you to chain an arbitrary number of layers together and allows them to call them in sequence on a given input. So the way this looks then is you can create a model, in this case I'm just calling it M, with these 2 layers in it. And you can evaluate both those layers all at once just by calling M. And you can see that this is exactly the same as doing it manually. We get the same answer, exactly the same down to floating point exactness. And in this case, I'm using the piping syntax of Julia to do these function calls, which is a nice way of expressing this, right? Because we're taking our feature vector, passing it to layer 1, passing it to layer 2, and then we get our output. So that is what chain does for us, and it couples it very nicely. So if you'll recall, in our last lecture, we created a model, defined our loss function, defined an optimizer, and then trained it. Well, all we need to do to make this a deep learning network is to update our model to have a chain of 2 dense functions. So let's use those 4 intermediate outputs that we'll have in our hidden layer. and have a second neural network that takes those 4 intermediate outputs and goes out to our 3 outputs to match our labels. And again, we'll just use a sigma activation function here. So that's all we need to do to update our single neural network into a deep neural network. So that trains this. And now if you'll recall, the way we trained this repeatedly, right, that goes through one iteration of our entire data set. To repeatedly train this, we created a kind of a dummy for loop and called it repeatedly. Well, our model is now far more complicated, so this is going to take more time. In fact, you can see how much time it's going to take by just asking Julia to time it. You can see that it takes about 0.3 of a second to train this. So of course, if we want to do this 1,000 times, that's 300 seconds. That's a long time to wait, 5 minutes. We don't have time for that. We need to do better. So how can we improve our efficiency here? Well, one way is through batching, and I can explain what that means here. So our data right now are set up as a 2,935 element vector, right? And the first element of our data is a tuple with our feature vector and our label vector, our one-hot vector as our label. So rather than, evaluating all of these individually, right, we can chain them together. Now, if you remember, in our previous lecture, we talked about matrix vector multiplications and how they looked and worked and how it was effectively, doing the dot product between the column of the vector and the rows of our matrix. Well, we can extend this concept so that way if we multiply by, say, a 2x2 matrix instead of a 2x1 vector, we end up with a 2-column output. And you can see that the first column is exactly the same as what we had when we did the matrix vector multiply. If we do the matrix multiply, the second column of our x is used to populate the second column of our output. And in fact, you can see this in general. The way this works is, this matrix multiplication is the same as doing a matrix vector multiplication, where we first take the first column of x as our first vector and our second column of x as our second vector. Oops, name my x there, and concatenate them together. And you'll see that that's exactly the same as what we did before. But what we're doing here is we have 2 matrix vector multiplications instead of, in this case, we're just doing 1 multiplication, and it's populating both columns for us. Now, matrix multiplications have been highly optimized over the past 3 or 4 decades. Lots of research has gone into it, both on your CPU as well as GPUs, which are largely matrix multiplication machines. They can do lots of matrix multiplications very rapidly and efficiently. So we can lean on all that great infrastructure by expressing our problem in terms of a matrix multiplication. Flux can help out with that by using this batch command, where it'll take all our x's. So remember, our first x's here is our feature vector, 0.7 and 0.3, and it takes that first feature vector and puts it as the first column. And our second feature is our second column, and so on and so forth. So we end up with a 2 by about 3,000 element array that describes all of our data all at once. And in fact, we can call our model on this. And everything we've done in our model, it works just fine with this. It's just changes our matrix vector multiplication to a matrix product. In that manner, we're able to see that the output of our model, when evaluated with this batched data set, is then a 3 by 3,000 array, where the first column is the output for our first x's. And you can see that this is exactly the same, where we have 500, 600, 90, 200ths, and those are exactly the numbers that we see. So this allows us to do this much more efficiently. Well, how much more efficiently, you might ask? We can time it. And here you can see we're over 100 times faster on the second run after compiling. So that is a huge optimization and a big win for us. So that is something that we want to take advantage of, because now instead of waiting 300 seconds, we can just wait 2 seconds to do 100 iterations or some such. So let's train this. Before, what we had, it was a for loop, right? We said for underscore in 1 to 10,000, and then flux.train, yada, yada, yada. So this was the way we did it before. Well, the other way we can express this, instead of writing a for loop, is with the iterators.repeated function. And what that does is it takes some value, doesn't matter what that value is, and it just repeats it a number of times. So we can repeat the string hi 3 times here. It returns something that's lazy. If you collect it, you'll see all 3 iterations here. So this is a way of structuring our data in a way that Flux can work with it, and we can repeat it many times, so that way Flux can walk through our data set multiple times as it takes that path down the loss hill. So we can ask what the current loss is of our data set, and you can see that we're at 0.19. You can keep training and see if we continue improving on our loss. Now, this is the training loss, right? I'm looking at the loss within the data that it's using to train the model. You'll also want to have, in general, a test set that's held out that you can test on. That's novel data that the model's not seen. So that way you're not cheating when you see how well your model performs, because you'll want to eventually probably run this model on novel data. So you'll want to make sure that you perform well on data that the model hasn't seen as part of its training process. But let's hold off there and let's visualize, see where our decision boundaries are falling. So we're imagining that the 0.5 value within our one hot vectors is going to be our decision boundaries. And you can see that, well, our decision boundaries aren't doing so hot right now. They are kind of not making too much sense. They're not encapsulating our data very well. So one way to address this would just be to go back and, hey, let's train some more. So let's train another 10,000 times, see if we continue walking down our gradient and see if we continue improving it. Once we've done that, we can see if our loss has improved, right? And that's how we'll know if we've kind of found the bottom of our valley yet, or if there's yet more improvements to be had. So once that is done, we can ask for the loss and see if it's better than 0.19. And indeed it is. It's 0.14 now, so that's significantly better. So let's see if our visualization is seeing any improvements where our decision boundaries are, our pseudo decision boundaries are. And sure enough, it looks like our decision boundary for our grapes is improving. It's starting to say, yes, everything up here is a grape, everything down here is not. Our bananas is getting closer, right? Maybe about half of this cluster is being says that it's a banana. And our apples, though, man, this line's having trouble. It's not sure where to put that, and it really needs to be not a line, but a curve that is able to do this. So how can we improve this besides just going back and running training over and over and over again? Well, there's a few things we can do. One of which is exploiting the known structure that our data, and particularly the model outputs, will have. So our labels and the model output. We know that those are one hot vectors, right? So we know that they're going to be between 0 and 1. So we can look at what our loss function looks like, for example. We're using the mean squared error. And we can look at what the loss function looks like compared to a known value. So let's say we want just, in this case, toy example, we're just looking at a 2-element categorization, but the concept is the same, where we have 1 and 0, and then we're going some distance away from that, right? And so our loss function is, as you'd expect for a mean squared error function, a parabola, where here's our correct output, where x is 0. That means that we end up with a 1, 0 vector, which matches our 1, 0 label. And anywhere away from that, we have some non-zero loss, which allows us to walk down that function, right? So that's good. That's what we want. But there's some extra things here, right? Really, all we want are numbers between 0 and 1. We don't really care about things that are negative or over 1. We want the model to eventually represent our labels in a well-defined manner. So we'd expect them to be bounded between 0 and 1. So in order to do that, there are some other functions, some other loss functions that are defined just on that range, on that domain, that would perform better for us. One such function is the cross-entropy function. Now there's a lot of information theory that goes behind cross-entropy and exactly how it works, but for this purpose you can just see that it totally blows away this parabola in terms of how rapidly the loss function ramps up as the answer gets more and more wrong. In fact, it asymptotes towards infinity as you get closer and closer to the completely wrong answer of a 0, 1 vector. So that's cool. And the other cool thing is that it's actually designed for, if you dig into the theory behind it, it's designed for probability distributions, which is exactly what we can think about our labels as, right? This is the probability of the first component being true, and this is the probability of the second component being true. So if that's the case, then not only do these things need to be bounded between 0 and 1, but they also should sum to a 1. So in order for it to represent a probability distribution, all the elements should sum to 1. That's not the case currently. In fact, we can see what the current model value is of x is of 1. You can see it's greater than 1. As we play around, you can look at the different feature sets. Generally, this isn't going to sum to 1. We've not told the model that we're actually doing something that should output a probability distribution. All we've said is that that final activation function is a sigmoid, which is bounded between 0 and 1. So all three elements are going to be bounded between 0 and 1, but they might sum to something that's different. So it might be nice to encapsulate some of that information. And there's another, So if we look at what the mean squared error is for a function that is close to our label. So here we have, going back to the 3 output labels. So this would be like, it's an apple, not a banana, not a grape. If we have a model that's close to that, you can see that the mean squared error is close to that. Again, and if we change this to a cross entropy, you can see that it also is a small number. Now, if we change this to be the wrong value, you can see that now the cross entropy is a very large number, whereas the mean squared error, as you would expect based on the plot above, it's a smaller number, and the gradients thereof are less steep, so you may converge a little slower. The other thing that we want to do, though, is we want to consider the output of our model as probabilities. So if we look at the output of our model and normalize it, so that way all 3 elements sum to 1, we can do that with a function called Softmax, which will normalize these. And again, there's a lot of information theory that goes behind this function, but suffice it to say that this normalizes it in a way that the sum between the 3 are going to be exactly 1. The other thing that it does is, remember that our model is currently bounded between 0 and 1 because we have a sigmoid activation function at the end. Well, what if our model wasn't bounded in that way? So if we had a 1, -1, 3, for example, as an output of our model, you can see that the softmax now has also normalized that. If we were to try to use cross entropy here directly with this output, you can see that we are outside of our safe domain for cross entropy, and you end up with a domain error because it's only well defined in cases where this is a probability distribution. And of course, this theoretical output vector does not represent a probability distribution. So the softmax function can help us do that. Now, one thing to note, though, is the softmax function allows normalization across the entire domain of real numbers, not just between 1 and 0. And in fact, if our model were to output exactly 1, 0, 0, and we were to transform it with the softmax function, well, it's going to normalize that in a way that we end up with maybe a 57% confidence that the first element is true. Well, that's because it's expecting to be able to, accept negative numbers and bigger differences and things like that. So we want to unconstrain our final activation function so that way it can output numbers across the entire domain. So that is a way that we can encapsulate a bit more information about the kind of task that we're doing in our model, in our deep learning model. So let's update our model. So before, this was what we were using before. We need to update this so that way we use the softmax function. Well, remember that chain just chains together the output from the previous argument and to input of the next, and it just calls them as though they were functions. So we can actually put the softmax function directly into this chain. And it will call it based on the output of the previous argument. And like I was saying, if the activation function of this previous argument is bounded to some small section of the range, well, then the softmax function isn't going to be able to do its job of normalizing. And we're going to be constrained to just a very small section of the domain. Really, we just want to have the identity function here. And remember why we were using a nonlinear function in the first place. Well, we were using it so that way we could chain together two neural networks in a way that the composition of the two doesn't collapse back down to a single linear function. So this nonlinearity is still extremely important, but this one we want to unconstrain to allow the softmax function to provide that normalization. And then we update our loss function. Instead of the mean squared error, we can use the cross entropy here. And the optimizer can remain the same with the stochastic gradient descent. So you can see how you can just slowly, iteratively refine your models in just a few lines of code. And we can train this again. And this time, let's train it with a little less data, 5,000 iterations instead of 10,000. So this will be kind of a tougher test, but see if we can perform better based on our changes that we've made. Once that's done, we'll plot our decision boundaries and check it out. So you can see maybe if I can scroll down, so now you can see that our model has been able to train, has able to encapsulate our data. It's starting to converge. We can tell that there's some work to be done yet, though, right? There's data points here that are entirely overlapping within their feature space. So there's no possible way that a model could ever detangle these unless you added more features. So you may want to see this and go back and add more features to your data set to improve your evaluation. But clearly this is doing much better. We've trained a deep neural network to encapsulate nonlinearities in our data and have been able to represent and in particular pick out these apples. So just as a quick recap, we defined our deep neural network simply as a chain of two neural networks. We then went back and improved on our algorithm by adding the softmax normalization, and in doing so, we're able to interpret the outputs of our model in terms of percentages and confidences, so that we can see how things are going. We're using the cross entropy loss function instead of the mean squared error function, but the core of our algorithm is essentially the same as the very first time that we did this in our very first lecture. We're just slowly, incrementally improving it and adding complexity. So that is deep learning with Flux.